Hi, I'm Remy Solis, consultant at Greenflex, and I'm going to talk to you about solar. Solar energy, especially photovoltaic, PV, technology, makes a lot of sense in the context of 5GDHC, fifth generation district heating and cooling, systems. 5GDHC is a revolutionary approach to providing heating and cooling services in urban areas by integrating advanced communication and control technologies with district energy systems. In the pursuit of a sustainable future, the world is increasingly turning towards innovative technologies to minimize energy consumption and reduce reliance on fossil fuels. One such groundbreaking solution is 5GDHC, which stands for Fifth Generation District Heating and Cooling. This advanced system aims to tackle the challenges of electricity peak consumption by optimizing the distribution of heat and cooling in urban areas. By doing so, it offers a promising pathway to decrease the use of fossil fuels and promote energy efficiency on a large scale. Traditional heating and cooling systems heavily rely on electricity to meet peak demands, resulting in increased greenhouse gas emissions and strain on the power grid. However, 5GDHC introduces a holistic and intelligent approach to address this issue. It combines the power of fifth-generation district heating and cooling networks with digital technologies, creating a more sustainable and responsive energy infrastructure. The core principle of 5GDHC is to balance the supply and demand of heating and cooling within a district. By leveraging digital control systems, advanced sensors, and predictive analytics, the system optimizes energy flows in real time, adapting to the changing needs of consumers. This dynamic approach allows for better load management, minimizing the peak electricity demand during extreme weather conditions or high occupancy periods. One of the primary advantages of 5GDHC is its ability to utilize waste heat from various sources such as industrial processes, data centers, and wastewater treatment plants. Instead of letting this valuable heat go to waste, the system captures it and redistributes it to meet the heating and cooling needs of buildings within the district. This integration of waste heat not only reduces reliance on fossil fuel-based heating but also promotes resource efficiency and the circular economy. Furthermore, 5GDHC supports the integration of renewable energy sources. By intelligently balancing the energy mix, the system can maximize the utilization of renewable resources like solar and geothermal energy. This integration of clean energy sources further reduces the carbon footprint associated with heating and cooling, contributing to the overall decarbonization efforts. In summary, 5GDHC represents a transformative approach to heating and cooling in urban areas, aiming to avoid electricity peak consumption and consequently reduce the use of fossil fuels. By leveraging advanced digital technologies, waste heat recovery, and renewable energy integration, this innovative system offers a sustainable pathway towards energy efficiency and a greener future. Embracing 5GDHC can lead us towards a more resilient and environmentally friendly energy infrastructure, ensuring a better quality of life for current and future generations. Using thermal storage and advanced demand-side management are two key strategies that can effectively reduce peak loads and optimize energy consumption in various sectors. Let's explore each of these approaches in more detail. 1. Thermal storage. Thermal storage is a technique that involves storing excess thermal energy during off-peak periods and utilizing it during peak demand periods. This approach helps to shift the energy load away from peak hours, reducing strain on the power grid and minimizing the need for additional fossil fuel-based generation. Thermal energy can be stored in various ways, such as A. Sensible heat storage. This involves storing heat in materials like water or rocks, which can be later extracted and used for heating or cooling purposes. B. Latent heat storage. This method utilizes the heat absorbed or released during a phase change, such as the melting and solidification of a material like ice or a phase change material, PCM. The stored energy can then be released when needed. C. Thermochemical storage. This approach involves storing heat through reversible chemical reactions that can release energy when required. Thermochemical storage offers high energy densities and long-term storage capabilities. By incorporating thermal storage systems into district heating and cooling networks, industries, and even individual buildings, it becomes possible to optimize energy usage and reduce peak loads. During periods of low energy demand, excess heat can be stored, and during peak hours, the stored heat can be utilized, thereby reducing the need for additional energy generation and minimizing reliance on fossil fuels. 2. Advanced Demand-Side Management, DSM. Demand-side management focuses on actively managing and optimizing the energy consumption patterns of end users. Advanced DSM techniques utilize real-time data, smart grid technologies, and digital control systems to shift or reduce peak loads in response to supply-demand imbalances or price signals. Here are some key strategies employed in advanced DSM. A. Time-of-use pricing. This involves implementing variable electricity pricing based on the time of day. By incentivizing consumers to shift their energy usage to off-peak periods when electricity is cheaper, peak loads can be reduced. B. Demand response programs. These programs enable consumers to voluntarily adjust their energy consumption in response to signals from the grid operator. Participants may receive financial incentives or other benefits for reducing their electricity usage during peak demand periods. C. Automated energy management systems. These systems utilize smart meters and connected devices to monitor and control energy usage in real time. They can automatically adjust settings or temporarily reduce power to certain devices during peak load periods, optimizing energy consumption without compromising comfort or productivity. D. Load shifting and load shedding. Load shifting involves moving energy-intensive tasks to off-peak hours, while load shedding involves temporarily reducing or shutting down non-essential processes during peak demand periods. These strategies help to flatten the demand curve and reduce stress on the grid. By implementing advanced DSM techniques, energy consumers can actively participate in load management, reducing peak demand and enabling a more efficient utilization of existing energy resources. This approach not only helps to reduce the reliance on fossil fuels, but also enhances grid stability and reliability. In conclusion, incorporating thermal storage systems and advanced demand-side management techniques are effective strategies for reducing peak loads and optimizing energy consumption. By storing excess thermal energy and intelligently managing demand, these approaches contribute to a more sustainable and resilient energy infrastructure, reducing the need for additional fossil fuel-based generation and promoting a cleaner and more efficient energy future. Producing electricity is a key strategy for 5GDHC to further reduce fossil fuel usage and greenhouse gas (GHG) emissions. Indeed, 5GDHC systems provide heating, cooling, and hot water to buildings in an efficient and sustainable manner. But, despite their efficiency, 5GDHC systems still rely on external energy sources, including fossil fuels, for electricity generation. The solution is clear. By producing their own electricity, 5GDHC systems can achieve greater energy independence and environmental sustainability. The benefits are reduced fossil fuel dependence. Generating electricity on site reduces the need for external energy sources, minimizing reliance on fossil fuels. Lower GHG emissions. Generating electricity locally allows for the integration of renewable energy sources, reducing overall GHG emissions. Enhanced energy resilience. Producing electricity on-site improves system resilience, ensuring a reliable and uninterrupted energy supply. There are many strategies for electricity production in D2 Grids projects. Solar power. Installing solar panels on buildings within the 5GDHC network can harness the abundant energy from the sun. Biomass energy. Implementing biomass power plants enables the use of organic waste materials to generate electricity. Geothermal energy. Leveraging geothermal heat pumps can tap into the Earth's natural heat to produce electricity. That is the reason why producing electricity within 5GDHC systems is a vital step towards achieving energy efficiency, reducing fossil fuel dependency, and mitigating GHG emissions. By embracing on-site electricity production, 5GDHC systems can lead the way towards a sustainable and resilient energy future. In addition to its contributions to raising the share of renewable heat, 5G systems can also play a significant role in achieving the goal of renewable electricity in Europe. These innovative systems integrate advanced communication and control technologies with district energy networks, offering several advantages for renewable electricity generation and utilization. If we take a look at the electricity mix in the countries involved in the D2 Grids project, there is a disparity, and we are still a long way from achieving the targets set by the European Union, 42.5% in 2030. Producing its own electricity can be a significant step towards improving a territory's energy autonomy and creating a shield against rising energy costs. With the advancement of renewable energy technologies and decentralized power generation, communities and territories now have more opportunities to generate their own electricity locally. This not only enhances their energy independence, but also brings various economic, environmental, and social benefits. One of the primary advantages of producing local electricity is the reduced dependence on external energy sources. Traditional energy supply chains often involve long-distance transmission and distribution, which are vulnerable to disruptions, transmission losses, and price fluctuations. By generating electricity within the territory, communities can become less reliant on these external factors, ensuring a more stable and secure energy supply. Renewable energy sources such as solar, wind, hydro, and geothermal power offer sustainable alternatives to fossil fuel-based electricity generation. Installing solar panels on rooftops, setting up wind turbines, or utilizing hydroelectric or geothermal resources can provide a territory with clean and renewable sources of energy. This helps mitigate environmental concerns associated with traditional energy generation, such as greenhouse gas emissions, air pollution, and climate change. Moreover, producing local electricity can contribute to economic growth and job creation within the territory. The installation, operation, and maintenance of renewable energy infrastructure require skilled labor, fostering employment opportunities in the green energy sector. Local businesses can also benefit from the growth of renewable energy industries, such as manufacturing, installation services, and maintenance and repair. Another significant advantage is the potential for energy cost savings. As energy costs continue to rise globally, producing electricity locally can act as a shield against these increases. Generating electricity from renewable sources can often result in lower operational costs in the long term, as the fuel sources, sunlight, wind, water, or heat from the earth, are free and abundant. Territories can potentially stabilize their energy expenses and reduce the financial burden on residents and businesses. Additionally, producing local electricity can promote community engagement and resilience. Local energy projects often involve citizen participation, such as community-owned solar installations or cooperatives. These initiatives empower communities to take control of their energy future, fostering a sense of ownership and involvement. In times of emergencies or natural disasters, local electricity generation can also provide a reliable source of power, enhancing the resilience of the territory's infrastructure and services. To realize the full potential of producing its own electricity, territories should adopt supportive policies and regulations. Governments can provide incentives and subsidies for renewable energy projects, simplify permitting processes, and establish net metering or feed-in tariff systems that enable the integration of locally generated electricity into the grid. Collaboration between local governments, energy companies, and community stakeholders is crucial for developing sustainable and effective energy solutions. In conclusion, producing its own electricity allows a territory to enhance its energy autonomy, reduce reliance on external sources, mitigate environmental impacts, create economic opportunities, shield against rising energy costs, and foster community resilience. By embracing renewable energy technologies and empowering local communities, territories can pave the way towards a sustainable and decentralized energy future. Solar production can revolutionize energy consumption in urban areas by harnessing the power of the sun and transforming buildings into sustainable energy generators. The concept of integrating solar panels on the roofs of various buildings within a city offers numerous benefits, such as connecting them to a heat network, creating a network of prosumers, consumers who also produce energy. This approach allows for the utilization of solar energy not only for the heat network but also for all the needs of the neighborhood or city. By installing solar panels on rooftops, buildings become active participants in energy production rather than solely energy consumers. This shift towards decentralized energy generation empowers communities to reduce their reliance on fossil fuels and contribute to a cleaner and more sustainable future. The integration of solar panels with the heat network presents a unique opportunity for leveraging solar energy effectively. Solar thermal panels can be installed to capture the sun's heat and convert it into usable thermal energy. This energy can then be fed into the heat network, providing a renewable source of heat for various purposes such as space heating, water heating, and industrial processes. Furthermore, the surplus solar energy generated by the rooftop panels can be shared with neighboring buildings and the wider community. Through advanced metering and grid integration systems, excess electricity can be fed into the local power grid, making it accessible for use by other consumers in the vicinity. This enables the concept of prosumers, where individuals and businesses can both consume and produce energy, fostering a sense of community and collaboration in the energy sector. In addition to serving the heat network, the solar energy produced on rooftops can be utilized for all the needs of the neighborhood or city. It can power street lighting, charging stations for electric vehicles, public buildings, and other communal facilities. By tapping into the abundant solar potential available in urban areas, cities can significantly reduce their carbon footprint and enhance their energy resilience. Implementing such a solar infrastructure requires collaboration between local authorities, building owners, energy companies, and residents. Incentives and support mechanisms can be established to encourage building owners to invest in solar installations, such as tax credits, subsidies, or favorable financing options. Awareness campaigns and educational initiatives can also play a vital role in promoting the benefits of solar production and fostering a culture of sustainable energy practices within the community. In conclusion, integrating solar production on the roofs of buildings in cities and connecting them to the heat network transforms consumers into prosumers, active participants in energy generation. This approach enables the utilization of solar energy not only for the heat network but also for all the needs of the neighborhood or city, reducing reliance on fossil fuels and fostering a more sustainable and resilient energy future. Before start the training, keep in mind that having an integrated approach of energy consumption to reduce GHG emissions and energy costs and increase the share of renewables with. Number 1. Have a complete and holistic view of energy consumption at a territory scale. Include the best practices for production, distribution, storage, and management of local renewable electricity in 5GDHC grid. Number 2. Create a local energy community with low carbon emissions for carbon intensity reduced at its lowest for a sustainable quality of service and making consumers become prosumers furthermore. Number 3. Curb energy costs on the long term for investments that provide a long-term visibility and protect the territory community from costs evolution. In order to address the various issues, this training course will be divided into 2 modules. Module 1. Technical Solutions for Solar Energy in 5GDHC. Number 1. Opportunities for solar energy. Number 2. Photovoltaics. Number 3. Thermal solar. Number 4. Hybrid, photovoltaics and thermal. Hashtag 5. Comparison of pilot sites. Number 6. Example of Plymouth. Number 7. Conclusion. Module 2. How to ensure that solar panels feed 5GDHC projects. Number 1. Capitalization call. Number 2. Main roles in self-consumption. Number 3. Governance in photovoltaics. Number 4. Comparison of pilot sites. Number 5. Conclusion. First of all, let's look at technical solutions for solar energy in 5GDHC. There are many opportunities for solar energy, but in this module we will focus on the following ones. Photovoltaic. Total injection and complete drawing off. Self-consumption or energy community. Partial self-consumption with sale of surplus to the grid and additional withdrawal. Collective self-consumption with possibility to sale of surplus to the grid and additional withdrawal. Hybrid self-consumption with possible sale of surplus to the grid and backup. Thermal solar. Individual or collective solar water heater. Hybrid solar, PV plus thermal. Photovoltaic, PV, technology is a method of converting sunlight directly into electricity using solar cells. These solar cells, typically made from semiconductor materials such as silicon, generate an electric current when exposed to sunlight. Photovoltaic systems, also known as solar power systems, have become increasingly popular as a clean and renewable energy solution. The basic building block of a photovoltaic system is the solar cell. Multiple solar cells are connected to form a solar panel or module, which is then interconnected to create an array. When sunlight strikes the solar cells, photons in the sunlight's energy excite electrons in the semiconductor material, generating a flow of electric current. This direct current, DC, can be used to power devices or stored in batteries for later use. Photovoltaic systems offer several advantages. First and foremost, they harness solar energy, a virtually unlimited and abundant resource. Sunlight is available in most regions of the world, making photovoltaics a viable option for electricity generation in various locations. Additionally, PV systems produce electricity without emitting greenhouse gases or other harmful pollutants, contributing to a cleaner environment and mitigating climate change. Photovoltaic technology has seen significant advancements and cost reductions over the years. Improved manufacturing processes and economies of scale have made solar panels more affordable and accessible to a wider range of consumers. This has led to widespread deployment of photovoltaic systems in residential, commercial, and utility-scale applications. PV systems can be deployed in various configurations depending on the specific needs and available space. Rooftop solar installations are common in residential and commercial buildings, where solar panels are mounted on the rooftops to capture sunlight. Ground-mounted systems are another option, particularly for larger installations or areas with limited roof space. Solar farms, consisting of large-scale arrays of solar panels, are deployed to generate electricity for the grid. To maximize the efficiency of photovoltaic systems, proper site selection and system design are essential. Factors such as the orientation and tilt angle of the solar panels, shading, and local weather conditions can affect the system's performance. Additionally, advancements in solar panel technologies, such as monocrystalline, polycrystalline, and thin-film cells, continue to improve efficiency and overall power output. Photovoltaic systems can also be integrated with energy storage solutions, such as batteries, to store excess energy generated during periods of high sunlight and use it during times of low sunlight or increased electricity demand. This enables greater self-consumption of solar power and enhances the reliability and flexibility of the system. Government incentives and policies, such as feed-in tariffs, tax credits, and net metering, have played a crucial role in promoting the adoption of photovoltaic systems. These incentives help reduce the upfront costs and provide financial incentives for generating solar electricity. In summary, photovoltaic technology is a clean and renewable energy solution that converts sunlight directly into electricity. It offers environmental benefits, energy independence, and cost savings, making it an attractive option for a wide range of applications. As technology continues to advance and costs decline, photovoltaics are expected to play an increasingly important role in the global energy transition. In the context of photovoltaic (PV) systems, an offset between production and consumption refers to the situation where the generation of solar energy from PV panels does not align perfectly with the immediate energy demands or consumption of the building or facility where the system is installed. This offset is primarily due to the intermittent nature of solar power generation, which depends on factors such as sunlight availability and weather conditions. PV systems generate electricity when sunlight strikes the solar panels, which then convert the sunlight into electrical energy. This energy can be used immediately to power the electrical loads within the building. However, if the PV system generates more electricity than what is being consumed at that moment, the excess energy needs to be either stored or exported to the grid. When there is an offset between production and consumption, it means that the PV system may produce more energy than what is needed during certain periods, such as sunny days or times when the energy demand is low. Conversely, it may produce less energy than what is required during periods of high energy demand or when sunlight is limited, such as during cloudy days or at night. To address this offset, there are several options available. 1. Grid-tied systems with net metering. In this setup, the PV system is connected to the electrical grid. When the system produces excess energy, it can be fed back into the grid, and the owner receives credits or financial compensation for the surplus energy. During periods of low PV generation, energy can be drawn from the grid to meet the building's needs. 2. Battery storage systems. Batteries can be used to store excess energy generated by the PV system during times of high production. This stored energy can then be utilized when the PV system is not generating enough electricity, such as during nighttime or periods of limited sunlight. Battery storage systems allow for greater self-consumption of solar energy and can provide backup power during grid outages. 3. Load shifting and energy management. By adjusting the timing of energy-consuming activities, such as running appliances or charging electric vehicles, to coincide with periods of high PV generation, the offset between production and consumption can be minimized. Energy management systems can be employed to automate this process, optimizing the utilization of solar energy. Efforts are also being made to improve the efficiency and reliability of PV systems, as well as to develop complementary renewable energy sources, such as wind power, to enhance the overall energy generation and reduce the impact of production consumption offsets in the renewable energy landscape. Thermal solar energy can indeed be interesting for 5GDHC, fifth-generation district heating and cooling, systems. 5GDHC is an advanced approach to heating and cooling buildings, which integrates various energy sources and utilizes low-temperature networks to distribute thermal energy. Here's how thermal solar can play a role in such systems. Solar thermal collectors. Solar thermal collectors capture the sun's energy and convert it into heat. These collectors typically consist of panels with tubes or channels that circulate a heat transfer fluid. The heated fluid can then be used directly or stored for later use in the 5GDHC system. Heat generation. Solar thermal collectors can serve as a heat source for the 5GDHC system, especially during sunny periods. The collected solar heat can be used to directly supply hot water or space heating needs. By utilizing solar energy, the system reduces reliance on conventional heating sources, leading to lower carbon emissions and increased energy efficiency. Thermal storage. One of the key features of 5GDHC systems is thermal storage. Excess solar thermal energy can be stored in well-insulated tanks or underground thermal reservoirs during periods of abundant sunlight. This stored heat can then be used during periods when solar energy generation is lower or when there is a higher demand for heating. Thermal storage ensures a continuous and reliable supply of heat, even during cloudy or nighttime conditions. Integration with other energy sources. Thermal solar can be integrated with other energy sources within the 5GDHC system. For example, when solar energy is insufficient, other heat sources like waste heat from industrial processes, geothermal energy, or heat pumps can be used to supplement the thermal energy supply. The integration of multiple energy sources provides flexibility and resilience to the system, optimizing its overall efficiency and reducing dependence on fossil fuels. Cost and environmental benefits. Solar thermal energy can help reduce the operational costs of a 5GDHC system by utilizing a free and renewable energy source. It also contributes to environmental sustainability by reducing greenhouse gas emissions associated with traditional heating methods. Additionally, solar thermal technology has advanced significantly in recent years, making it more efficient and cost-effective to implement. By incorporating thermal solar energy into a 5GDHC system, it becomes possible to leverage the abundant energy provided by the sun and create a more sustainable and efficient heating and cooling infrastructure for buildings and communities. Hybrid PV plus thermal systems, also known as PVT systems, photovoltaic thermal systems, combine photovoltaic, PV, and solar thermal technologies in a single integrated system. This hybrid approach aims to maximize the overall energy efficiency of solar energy conversion, as it allows for simultaneous generation of both electricity and thermal energy from the same solar panel. Here are some key points about hybrid PV plus thermal systems and their benefits. Principle of operation. A hybrid PV plus thermal system typically consists of a standard PV module with a heat collector attached to its back surface. The PV module generates electricity from sunlight, while the heat collector absorbs the excess heat and transfers it to a fluid circulating through the collector. This heat can be utilized for various applications, such as space heating, water heating, or industrial processes. Increased energy efficiency. By capturing the waste heat from PV modules, hybrid systems can achieve higher overall energy conversion efficiency compared to standalone PV systems. Traditional PV modules tend to heat up during operation, which reduces their electrical efficiency. By extracting this heat and utilizing it, hybrid systems can effectively cool the PV cells, maintaining their performance and improving the overall energy output. Dual energy output. The integration of PV and thermal technologies allows for simultaneous generation of electricity and thermal energy. This dual energy output increases the overall energy yield per unit area of the system, making it a more efficient use of available space. This is particularly advantageous in applications where both electricity and heat are required, such as residential buildings, commercial facilities, and industrial processes. Improved PV module performance. PV modules and hybrid systems benefit from the cooling effect provided by the heat extraction process. As the modules remain cooler, their electrical performance is enhanced, leading to increased electricity generation. This cooling effect can help mitigate the negative impact of high temperatures on PV module efficiency, which is a common issue in many sunny regions. Space and cost savings. Since a hybrid PV plus thermal system combines two technologies into one, it can potentially reduce the overall installation footprint and associated costs compared to separate PV and solar thermal systems. This is particularly beneficial in situations where space is limited or expensive, as it allows for the dual utilization of available area and infrastructure. System integration. Hybrid PV plus thermal systems can be integrated into existing PV installations, making it a viable option for retrofitting or upgrading existing solar power systems. By adding the heat collector to the back of the PV modules, the system can be easily integrated without significant modifications to the existing infrastructure. Environmental benefits. Hybrid systems contribute to the reduction of greenhouse gas emissions by utilizing solar energy to generate both electricity and heat. This leads to a decreased reliance on fossil fuels for heating applications and a lower carbon footprint overall. It's important to note that the performance and benefits of hybrid PV plus thermal systems can vary depending on factors such as location, system design, heat utilization methods, and local climate conditions. The feasibility and economic viability of implementing such systems should be evaluated on a case-by-case basis, considering factors such as energy requirements, available space, and financial considerations. In the context of PV systems, total injection and complete drawing off refer to two different scenarios related to the generation and consumption of solar energy. 1. Total injection. Total injection occurs when a PV system generates more electricity than is being consumed on-site. In this scenario, the excess energy is sent back to the electrical grid. This is typically achieved through a process called net metering or feed-in tariff. The surplus electricity is fed into the grid, and the PV system owner is usually credited for the exported energy, which can offset their electricity bills. The amount credited varies depending on local regulations and agreements with the utility company. 2. Complete drawing off. Complete drawing off refers to a situation where the electrical energy consumed on-site exceeds the amount of electricity being generated by the PV system. When the PV system cannot meet the total energy demand of the property, the additional energy needed is typically drawn from the electrical grid. In this case, the PV system partially covers the energy needs, but the deficit is supplemented by the grid supply. It's worth noting that the specific terms total injection and complete drawing off may not be widely used in the PV industry. However, the concepts they represent are relevant in understanding the dynamics of energy generation and consumption in PV systems. Self-consumption in PV, photovoltaic, refers to the utilization of solar energy generated by a PV system directly on site, rather than exporting it to the electrical grid. It involves maximizing the consumption of the solar electricity within the property where the PV system is installed, reducing the reliance on grid-supplied electricity. The concept of self-consumption is driven by the desire to increase energy independence, reduce electricity bills, and promote sustainable energy practices. By consuming solar energy on site, PV system owners can benefit from the following advantages. 1. Cost savings. Self-consumption allows users to offset their electricity purchases from the grid with free solar energy. As a result, they can reduce their electricity bills and potentially achieve significant long-term savings, depending on the size of the PV system and energy consumption patterns. 2. Energy independence. By generating their own electricity, PV system owners become less dependent on the grid. This is particularly valuable in areas with unreliable or expensive grid power or during power outages. Self-consumption increases energy resilience and provides a degree of self-sufficiency. 3. Environmental benefits. Utilizing solar energy on site reduces the reliance on fossil fuel-based electricity generation, leading to a decrease in greenhouse gas emissions and environmental impact. Self-consumption contributes to a more sustainable and cleaner energy mix. To achieve high levels of self-consumption, several strategies can be employed. A. Load shifting. By shifting high-energy consuming activities to daylight hours when the PV system is generating electricity, such as running appliances, charging electric vehicles, or heating water, users can maximize self-consumption. B. Energy storage. Installing a battery storage system alongside the PV system enables the storage of excess solar energy for use during periods of low or no solar generation, such as at night or during cloudy days. Energy storage enhances self-consumption by maximizing the utilization of solar energy throughout the day. C. Energy management systems. Smart energy management systems can optimize self-consumption by intelligently controlling energy flows within a property. These systems can prioritize the use of solar energy, automatically adjust consumption based on solar availability, and provide real-time monitoring and control. D. Energy efficiency. Improving the energy efficiency of appliances, lighting, and building systems can reduce overall energy consumption. Energy-efficient practices, such as using energy-saving appliances or implementing efficient building design, complement self-consumption efforts by reducing the total energy demand. Self-consumption in PV systems aligns with the broader goals of renewable energy deployment, energy conservation, and sustainable development. By maximizing the utilization of solar energy on site, individuals, businesses, and communities can reduce their carbon footprint, save on energy costs, and enhance energy resilience. In France, both over-the-counter (OTC) transactions and power purchase agreements (PPAs) are possible mechanisms for buying and selling electricity generated by renewable energy sources, including photovoltaic (PV) systems. 1. Over-the-counter (OTC) transactions. OTC transactions refer to the direct buying and selling of electricity without the involvement of an organized exchange. In France, OTC transactions for renewable energy can occur between renewable energy producers, such as PV system owners, and electricity consumers or off-takers. These transactions are typically based on bilateral agreements and negotiated between the parties involved. OTC transactions offer flexibility in terms of contract structures, pricing, and terms, allowing for customized agreements to meet the specific needs of the parties. OTC transactions can benefit PV system owners by providing them with alternative avenues to sell the excess electricity they generate. Instead of relying solely on feed-in tariffs or net metering schemes, PV system owners can explore direct OTC transactions with interested buyers, including commercial and industrial consumers, municipalities, or other electricity consumers seeking to increase their renewable energy procurement. 2. Power Purchase Agreements, PPAs. Power purchase agreements, PPAs, are long-term contracts between electricity generators and buyers, specifying the terms and conditions for the sale and purchase of electricity. PPAs provide a stable and predictable revenue stream for renewable energy projects, including PV systems, by establishing a fixed price or pricing structure for the electricity generated over a defined period. In France, PPAs have gained popularity as a means of supporting renewable energy deployment. The government has introduced competitive tenders, such as the CRE, Commission de Régulation de l'Énergie, tenders, to enable developers of renewable energy projects, including PV installations, to secure long-term PPAs. These PPAs can be signed with utilities, energy suppliers, corporate off-takers, or other entities willing to purchase renewable energy. PPAs offer benefits to both PV system owners and buyers. For PV system owners, PPAs provide revenue certainty, improve project bankability, and offer a stable income stream over an extended period, typically ranging from 10 to 20 years. For buyers, PPAs contribute to their sustainability goals, help diversify their energy sources, and potentially offer cost savings over the long term. It's important to note that the specific regulations, market structures, and contractual arrangements for OTC transactions and PPAs in France may evolve over time. It's advisable to consult with relevant authorities, energy market participants, or legal experts for the most up-to-date information and guidance on engaging in OTC transactions or negotiating PPAs for PV systems in France. Let's see a comparison of pilot sites, different orientations and choices for photovoltaic systems, Paris versus Glasgow. Glasgow still under consideration, but as you can see, the thinking and the possibilities are different. I'm not going to dwell on this table any longer, as it's the diagram on the next slide that interests us. It should be noted that Glasgow first installed the system on the ground and then on the roof of a building for technical reasons. Let's look at a comparison of pilot sites, different orientations, and choices for photovoltaic systems. For Paris, the type of installation chosen here is collective self-consumption. Unlike individual self-consumption, there are several users of the electricity produced, the common parts of the Seekins buildings, as well as the heating and cooling network equipment. In general, Seekins favors either the total resale of its production to EDF or individual self-consumption with resale of the surplus to EDF. This avoids certain administrative and legal complexities and avoids the uncertainty of actual electricity production. Collective self-consumption presents complexities when it comes to defining the distribution of production and billing arrangements. However, the fact that they are involved in a large-scale project means that we have more time to deal with them and to carry out a study of actual production. For Glasgow, it is an important component of the project because it helps them to reduce the electrical load associated with the heat pumps so they can locally generate electricity as part of the overall network. In the initial stages of the project, what they are going to deliver is a ground-mounted solar array. That will take a very significant area within the development, and it will give a very clear indication to people visiting the site of what they are delivering. So those solar panels will then help provide locally generated electricity. They will also have battery storage as part of that. Then, as the master plan develops out across the site and they deliver for the buildings, they will then relocate the solar panels from the ground to the individual buildings, and it means that what they are doing in the very early stages of the project is really future-proofing the overall concept. Plymouth proceeded in 3 phases. The first consisted of installing photovoltaic systems, as shown on the diagram spread over several buildings. Council House Solar 90 kWp generating about 85 megawatt-hours per year. Guildhall has a 196 kilowatts generating drawing 479 megawatt hours per year of heat and drawing 191 megawatt hours per year of electricity. CHP generates 435 megawatt hours per year of heat and generates 234 megawatt hours per year of electricity. The aim was clear: to maximize local electricity production with storage to power heat pumps. The second phase was to take advantage of the solar surplus to store it and use it later with private wire, having multiple demand, including heat pumps, balanced with solar and batteries makes for well-distributed local network that relies less on the grid. Batteries help smooth the generation peaks with the time-offset demand peaks. This means that when the sun is shining, the heating may be less, but it can be stored to be used when the sun goes down and more heating needed. This is the biggest installation for Plymouth, Ballard House Solar alongside heat pump. Here's a perfect example of a double centralized installation with heat and electricity production. Heat pump is 196 kilowatts generating 608 megawatt hours per year of heat and drawing 216 megawatt hours per year. It is also water source for future connection to heat network. Solar is 64 kWp generating 61 megawatt hours per year, but mostly in summer. Insulation reduces the heat needed by 99 megawatt hours per year, mostly winter. In conclusion, benefiting from the best practices for production, distribution, storage, and management of local renewable electricity are: solar energy solutions, power to heat, self-produced renewable electricity to provide electricity to electric installations of the 5G grid, heat pumps, to other consumers of the district, housings, stores, electric mobility, etc. Thermal/PVT hybrid solar panels to produce domestic hot water in complementarity with heating from the grid. Storage facilities, optimizing the local use of the energy produced and distribution to other consumers and producers through storage. Thermal storage, electric storage, smart monitoring and control, intelligent and real-time balance between demand and supply to allow for various operational models, providing green electricity to the thermal grid to other consumers, selling surplus energy to electricity grid operators, storing energy to balance fluctuations. Let's talk now about the Module 2, how to ensure that solar panels feed 5G DHC projects. If you take over here, we strongly invite you to take over the part on different ways to enhance electricity produced with photovoltaic in the previous training. Let's talk briefly about capitalization call and more especially strengthening the synergies between DHC and electricity networks in cities. As a result of the second capitalization call, in addition to the main project work on the heating and cooling dimensions of these closed energy grids, the D2 Grids Consortium will now also work on better integration of electrical uses and local renewable electricity production capacities to improve the decarbonization of 5G DHC networks. Greenflex will be the leader of this new capitalization work package, which is composed of 7 partners from the initial consortium: Midgenwaterby.v, Asper Investment Management, Clyde Gateway, Open University, Construction 21, Vito and Greenflex, and 4 new partners: Engie Services Netherlands, Scottish Water Horizons, LLC and Associates Lawyers, and the French social housing company Seekins. The consortium will work on combining best practices in 5G DHC networks with best practices in local renewable electricity generation, distribution, storage, and management. This will allow the creation of more decarbonized multi-carrier local energy communities, delivering high-quality service and a competitive business model for local producers and consumers. In utilizing multi-energy dynamics, this will enable us to integrate the lessons learned from the addition of collective self-consumption photovoltaic to 5G DHC projects in the different countries concerned. The consortium will work to demonstrate the technical, legal, economic, and organizational relevance of integrating local renewable electricity and heat production with local needs for heating, cooling, and electricity from buildings, urban structures, or even charging stations for electric vehicles, and considering the associated possibilities for better flexibility, reducing peak demand, or utilizing storage. Beyond its technical dimension, the project will study the contracting models for sharing locally produced energy as well as the associated economic models, financial models, revenue from energy sales, etc., in order to disseminate the lessons learned. 3 of the D2 Grids pilot sites in Glasgow, UK, Brunsum, Netherlands, and Paris-Saclay, France, will be testing the synergies between electricity networks and heating and cooling grids. One of the challenges will be to turn these into models of best practice to encourage future project developers to consider integrated 5G DHC networks as a solution for their energy transition needs. This will encourage, in line with the goals of the D2 Grids project, an increase in the share of renewable energies and decarbonization in cities and territories in Northwest Europe. There are 3 main roles in self-consumption projects which can be taken by one or several stakeholders. Producer, he exploits the plant's products. Owner of the electricity produced. Consumes or resells it to an aggregator or another consumer. Consumer, he consumes the plant's products. He consumes electricity. If he produces the electricity he consumes, he is a self-producer. Investor, he operates a production asset. Power plant owner. If he makes the power plant available to the producer to produce electricity, he is a third-party investor. Photovoltaic systems can be deployed with or without a third-party investor. The choice between these options depends on various factors such as the financial situation of the project owner, the availability of capital, and the desired level of involvement in the project. Self-investment. If a project owner has sufficient capital or access to financing, they can choose to invest in a photovoltaic system themselves. In this case, they would bear the upfront costs of purchasing and installing the PV panels, inverters, and other necessary equipment. They would also be responsible for the operation, maintenance, and any associated risks or benefits of the system. The project owner retains full ownership and control over the PV system and reaps all the financial benefits, including electricity savings, potential revenue from selling excess power back to the grid, and potential incentives or tax credits. Third-party investment. Alternatively, a project owner can choose to involve a third-party investor who provides the upfront capital for the PV system. This arrangement is commonly known as a power purchase agreement, PPA, or solar lease. In a PPA, the investor owns and operates the PV system, and the project owner agrees to purchase the electricity generated by the system at a predetermined rate over a specified period. The investor typically handles the installation, maintenance, and any associated risks. This option allows the project owner to benefit from solar energy without the need for upfront capital or the responsibilities of ownership. However, the financial benefits may be shared with the investor, and the project owner may have fewer opportunities for customization or control. Both options have their advantages and considerations, and the best choice depends on the specific circumstances of the project owner. It is advisable to consult with professionals, such as financial advisors or solar energy experts, to determine the most suitable approach based on factors like financial goals, risk tolerance, and desired level of involvement. In the case of full injection, the project owner would bear the entire cost of the photovoltaic system, including the purchase and installation of the PV panels, inverters, and associated equipment. They would also be responsible for the ongoing operation, maintenance, and any associated risks. By fully investing in the photovoltaic system, the project owner retains complete ownership and control over the system. They would benefit from all the financial advantages, including electricity savings, potential revenue from selling excess power back to the grid, and potential incentives or tax credits. This option allows the project owner to have maximum control over the system, customization options, and the ability to optimize the financial returns from the investment. However, it is important to note that full injection requires significant upfront capital or access to financing. The project owner must also consider factors such as the payback period, return on investment, and ongoing maintenance costs. It is advisable to conduct a thorough feasibility study and consult with solar energy experts or financial advisors to assess the financial viability and potential benefits of a full injection photovoltaic project. Individual self-consumption photovoltaic refers to a system where an individual or household installs a photovoltaic system to generate electricity for their own consumption. The electricity produced by the PV panels is primarily used to power the individual's home or property, reducing the reliance on the grid and potentially lowering energy costs. In an individual self-consumption PV system, the generated electricity is consumed in real time as it is produced. The excess energy that is not immediately consumed can be stored in batteries for later use or fed back into the grid if a net metering or feed-in tariff scheme is available. Net metering allows individuals to receive credits or compensation for the excess energy they feed back into the grid, which can offset the energy they consume from the grid during times when their PV system is not producing enough electricity. The benefits of individual self-consumption photovoltaic systems include 1. Energy cost savings. By generating their own electricity, individuals can reduce their reliance on grid-supplied energy, leading to potential cost savings on utility bills. 2. Energy independence. PV systems allow individuals to produce their own clean energy, reducing their dependence on fossil fuel-based energy sources and contributing to a more sustainable future. 3. Environmental impact. Photovoltaic systems generate electricity from renewable sources, resulting in reduced greenhouse gas emissions and a smaller carbon footprint. 4. Grid resilience. During power outages or disruptions, individuals with battery storage capabilities in their PV systems can have access to backup power, enhancing their resilience and reliability. 5. Incentives and support. Depending on the location, individuals may be eligible for various incentives, such as tax credits, grants, or rebates, to offset the costs of installing a self-consumption PV system. It is important for individuals considering self-consumption PV systems to evaluate factors such as the available sunlight, the size and capacity of the system required, upfront costs, available incentives, and any applicable regulations or permits. Consulting with solar energy professionals or installers can help individuals design and install an optimal PV system for their self-consumption needs. Collective self-consumption photovoltaic refers to a system where a group of individuals or entities collectively install and share the benefits of a photovoltaic system for their own consumption. This approach allows multiple participants to pool their resources and jointly invest in a shared solar energy project. In a collective self-consumption PV system, the generated electricity is consumed by the participants in real time as it is produced. The electricity can be utilized to power homes, businesses, or other shared facilities within the collective. Similar to individual self-consumption, excess energy can be stored in batteries or fed back into the grid if net metering or feed-in tariff schemes are available. The benefits of collective self-consumption photovoltaic systems include 1. Cost sharing. By pooling resources, participants can collectively invest in a larger PV system, which may be more cost-effective compared to individual installations. The initial costs, such as purchasing equipment and installation, can be divided among the participants, reducing the financial burden on each individual. 2. Increased access. Collective self-consumption allows individuals who may not have suitable rooftops or properties for solar installations to still benefit from solar energy. Participants can collectively choose a location, such as a shared building or a community solar farm, where the PV system is installed. 3. Shared savings. The electricity generated by the collective PV system can result in cost savings for all participants. Each participant's share of the generated electricity can offset their individual energy consumption, potentially leading to reduced utility bills. 4. Community engagement. Collective self-consumption projects promote community engagement and collaboration. Participants work together towards a common goal of clean energy generation and can develop a sense of ownership and shared responsibility. 5. Environmental impact. Similar to individual self-consumption, collective self-consumption PV systems contribute to a reduction in greenhouse gas emissions and promote the use of renewable energy sources, thereby benefiting the environment. It is important for participants to establish clear agreements and legal frameworks regarding the management, operation, and sharing of costs and benefits within the collective self-consumption project. Consulting with solar energy professionals, legal advisors, or community organizations experienced in collective energy projects can help guide the development and implementation of such initiatives. Hybrid autoconsumption in photovoltaic refers to a system that combines solar photovoltaic panels with energy storage and a grid connection to optimize the self-consumption of solar energy and enhance energy independence. In a hybrid autoconsumption PV system, the solar PV panels generate electricity from sunlight. This electricity is first used to power the electrical loads within the premises where the system is installed. Any excess energy that is not immediately consumed is directed to charge energy storage systems such as batteries. These batteries store the excess energy for later use, typically during periods when the PV system is not generating electricity, such as nighttime or during cloudy weather. The key components of a hybrid autoconsumption PV system include 1. Solar PV panels. These panels convert sunlight into electricity and generate power for immediate consumption. 2. Energy storage system. Batteries are used to store excess electricity generated by the PV system. The stored energy can be used when the PV system is not producing electricity, ensuring a continuous power supply and reducing dependence on the grid. 3. Grid connection. The system remains connected to the grid, allowing for the import of electricity during periods of high demand or low solar generation and the export of excess electricity back to the grid when the batteries are fully charged. The benefits of hybrid autoconsumption photovoltaic systems include 1. Increased self-consumption. By storing excess energy in batteries, the system enables a higher level of self-consumption, reducing the reliance on the grid and maximizing the use of solar energy. 2. Energy independence. The combination of solar PV panels and energy storage systems promotes greater energy independence, allowing for a more reliable and consistent electricity supply even during grid outages or periods of low solar generation. 3. Load shifting. The stored energy can be used during peak demand periods or times when electricity prices are high, helping to reduce overall energy costs. 4. Resilience. Hybrid systems with energy storage provide backup power during power outages, ensuring critical loads can continue to operate. 5. Environmental benefits. By maximizing self-consumption of solar energy, hybrid autoconsumption systems contribute to a reduction in greenhouse gas emissions and promote the use of renewable energy sources. It is important to design and size the hybrid autoconsumption system appropriately to meet the energy needs of the premises and consider factors such as the capacity of the PV panels, battery storage capacity, and expected energy consumption patterns. Consulting with solar energy professionals or system integrators can help ensure an optimized design and installation of a hybrid autoconsumption photovoltaic system. Different countries mean different photovoltaic markets. Focus on France and AMP, Belgium. In France, self-consumption. Individual self-consumption when the PV installation is directly connected to the internal electric installation. When there are two different actors, it is collective self-consumption. Restricted collective self-consumption when the consumption is shared between consumers of the same building. Extended self-consumption when the actors are not all in the same building, but within a perimeter of 2 kilometers diameter. In Belgium, energy sharing. Collective self-consumption in an apartment or an energy community is called energy sharing. Collectively own the production. No payments for energy. Collective consumption through 2 or more peers through payment is called energy selling. Peer-to-peer 1-to-1, no constraint on energy supplier. P2P 1-to-many, need to have the same energy supplier. Let's have a look for the engagement in this scheme now. Seekins engage itself to self-consume first electricity generated by PV panels for the common area needs of its buildings, and to sell surplus to the APAP's grid to the minimum price for financial equilibrium, to guarantee local, non-polluting, affordable, and financially stable electricity for both its occupants and all users of the grid. This solution allows the entire production to be used and avoids the need for storage. Follow the efficiency of its system to ensure the maximum of electricity generated. communicate the results of its production, and share best practices to enable replication and improvement to large scale to EPAPs or any other grids. Clyde Gateway, Glasgow, will continue to explore how to maximize deployment of renewable electricity generation at the pilot site and options to increase these over time, including the use of storage of both electricity and heat. They will do this alongside partners including Scottish Water Horizons and British Geological Society, who have a geoenergy observatory looking at heat storage in disused mines in the nearby Cunnagar Loop Clyde Gateway Regeneration Program, and in discussion with current and future customers about their energy requirements. Further consideration is being given to increasing the overall capacity available in the heat network through upsizing the abstraction system and heat exchanger, which will be dependent on demand-side timescales. The D2 Grids pilot project envisaged connection of up to 3 buildings initially, but with a clear view that the full site would be capable of developing 100,000 square meters of office space to be connected. This remains the intention for the project to scale up and make these further connections as and when they become available. There is also the scope to explore more diverse end users and, in particular, the incorporation of residential development is being evaluated against the system operation and requirements as part of next stage connections. Increasing future customer connections is the largest focus area of future engagement to ensure mitigation of the revenue deficit position of project and to improve the return on investment (ROI) of the project. Smart technology is being utilized to manage the interface between the power and thermal grids to manage the cost of electricity and optimize the commercial position. This will ensure continual improvement to overall efficiency of project operations and may help with improving the economies of scale for the project for current and future customers. In conclusion, governance plays a critical role in the successful implementation and operation of photovoltaics in fifth-generation district heating and cooling systems. The integration of PV into 5G/DHC systems requires a coordinated and effective governance framework to address various aspects, including policy development, regulatory mechanisms, stakeholder engagement, and technical standards. Firstly, policy development is crucial to set clear goals and targets for PV integration in 5G/DHC systems. Governments and relevant authorities should establish supportive policies that incentivize the adoption of PV technologies, such as feed-in tariffs, tax incentives, or subsidies. These policies should be designed to promote the deployment of PV in 5G/DHC systems and facilitate the transition towards a low-carbon energy system. Secondly, effective regulatory mechanisms are necessary to ensure the smooth integration of PV into 5G/DHC systems. This includes establishing interconnection standards and grid integration rules to enable the seamless integration of PV-generated electricity into the district heating and cooling networks. Clear guidelines for the installation, operation, and maintenance of PV systems should also be established to ensure safety, reliability, and performance. Thirdly, stakeholder engagement is vital to create a collaborative governance approach. Engaging various stakeholders, including local communities, energy providers, technology suppliers, and research institutions, fosters a shared understanding of the benefits and challenges associated with PV integration in 5G/DHC systems. Collaboration and active participation of stakeholders can lead to better decision-making, effective project planning, and successful implementation. Lastly, technical standards play a crucial role in ensuring the interoperability and compatibility of PV systems within 5G/DHC infrastructure. Standardization of components, performance metrics, and system design guidelines will facilitate the efficient integration and operation of PV systems in 5G/DHC networks. This will also contribute to ensuring the quality, safety, and reliability of the overall system. In summary, the governance framework for photovoltaics in 5G/DHC should encompass supportive policies, effective regulations, stakeholder engagement, and technical standards. By establishing such a framework, governments, regulatory bodies, and stakeholders can collaboratively drive the successful integration of PV into 5G/DHC systems, leading to enhanced sustainability, energy efficiency, and the transition to a clean energy future. Thank you for your attention. Do not hesitate to visit us at 5gdhc.eu.